All right, welcome back to pycse. Today I want to talk a little bit about nonlinear regression and confidence intervals on the parameters. So it's going to be pretty easy to do the nonlinear regression in Python, and we'll go through a couple of methods for it. And what's not that easy, at least out of the box, is estimating the confidence. So here is the kind of schematic of what we'll do today. We'll have data that looks like this. We're going to fit this function through the data. It looks like this red line. And the question is, how confident are we in these parameters? So a is going to be the value that it plateaus to, because e to the minus bx goes to 0 and y is just equal to a. So when we estimate a, we want to know how sure are we about it, like what's the real value of a. So that's our goal, is to fit this function to this data. So this data here is just given by two arrays, and we can make a plot easy enough with matplotlib. So here we just do blue circles, we add some x labels and y labels, and the data roughly looks like this. So when we do a nonlinear regression, it's basically a minimization of some squared errors that has to happen, and we have to make some initial guesses. And so just by inspection, we could assume here that this is kind of plateauing, maybe around 220. So we could say A is going to be about 220. And you have to do a little bit of math to figure out that a good guess for B is something on the order of 0.5 to 1. I'm not going to do that so that we can concentrate instead on how to make these fits. All right, so in curvefit, what we have to do is define a model function. So let's go ahead and do that. Model, and it depends on x, and you have to put in positional parameters for all of the different parameters that are in there. And here we're just going to return a times np.exp of minus b times x, and this should be 1 minus that, and that's our simple model, just like that. Okay, so this is what we want to fit to the data, and then let's make sure we imported numpy here, and then let's import curvefit. All right, so with curvefit, all we have to do is we'll write out curvefit, and we'll give it the model, the x data, the y data, and we need to make an initial guess. So I said earlier something like 220, and 1 is a reasonable guess. And if you run this, then it will output the two parameters. So our parameters turn out to be 213 and about 0.5. And then we get this other thing that is called the covariance matrix. So let's go ahead and store those in some variables here. And we'll print the pars, and we'll look at pcov. Let's say with np.printOptions, precision equals 3, we'll print this. All right, so that gives us this thing that's called the p-covariance, and if you read curvefit, what you find out is the diagonal of this is related to the standard errors associated with each one of these parameters. All right, so we could do this, print, we'll just do np.square root of the diagonal of p-covariance, and that will give us two numbers, 12.35 and 0.1. Those are associated with the standard error associated with the estimate of 213 and 0.54. So the standard error is roughly like around a 68% confidence interval. That's one plus or minus 1 standard deviation accounts for, I think it's about 68% of the variance, and plus or minus 2 standard deviations is about 95%. Now, we can't use these numbers, quite exactly. This is an underestimate of the true error because we only have a couple of points, 1, 2, 3, 4, 5, 6. And so what would be typical to do here is calculate the student t values, the t multiplier, and then that number is typically bigger than 1, and multiply it on here to get to the desired confidence interval. And it's a little bit tedious to do that, especially if you have to do this, every single time and calculate the degrees of freedom that are associated with. We have 2 parameters, and now I can't remember, 7 data points, so 5 degrees of freedom, and all of that can be done. It's just tedious. Now, before we go on, I think it's always a good idea to plot your data. So let's make a plot of the data again. And we'll add to it a fit. So let's say x equals np.linspace 0 to let's extrapolate out to 20, and then let's add a plot of the fit. And we'll use the star parse operator to unpack this array up here into A and B, and we'll see how good our fit is. Except that I have missing a parenthesis. Okay, so here's our fit in the light blue line. It comes out and it plateaus again because e to the minus bx goes to 0, and all that's left is a, and a is a constant at about 213. But you see there's noise in here, and if you look up here at this 12.35, you might add plus or minus 12 to this number to have a plus or minus 1 standard deviation of expectation, or plus or minus about 24 off the top of our head. So it's 213 plus or minus 24 is a lower bound on the uncertainty, since we're not yet accounting for the extra uncertainty due to the small number of data points. All right, let me show you how it works with nlinfit. So nlinfit is a function in pycse, and that is a package I wrote for doing exactly this kind of thing. So let's import nlinfit. And it has a very similar signature as curvefit. In fact, it is only, let's look at it. Let's look at the actual code that gets done. So it takes a model, x, y, and the initial guess. So this is exactly the same as curvefit, and then you could choose a confidence interval. And in fact, the first thing we do is a curvefit here, but then we estimate the number of data points and the number of parameters, calculate the degrees of freedom, get the student t-value, and then once we have the standard errors in here, then we just calculate it like this. So this is all it takes to get a good estimate from the data that we have, but if you do this a lot, you don't want to be remembering all of these little details. All right, so the way we use it here then is we pass our model, pass in x, pass in y, pass in our initial guess, and the default is going to be 95% confidence, and so we can run this and we get all of those things out. So let's put these into variables. This returns 3 things: the parameter estimates, the confidence intervals, and the standard error associated with each one. So let's look at them one at a time. So these are the same numbers we got before. That shouldn't be surprising because, oh, this should be PCI. That shouldn't be surprising because we did exactly the same fit. And now we see the true confidence intervals here, and the confidence interval that we might be able to say at 95% is the true value of A is between 179 or 180 and 248. And so this range is a little bit bigger than plus or minus 12.35 times 2. And that is to account for the fact that we have additional uncertainty for only having 5 degrees of freedom in our analysis. All right, and the last thing I want to talk about is lmfit. So lmfit is a library. Let's look at it over here. So it's a Python library that you can install for doing nonlinear least squares, minimization, and curve fitting, and it has a lot more features than nlinfit. So nlinfit was really designed to mimic the behavior of a MATLAB function that gave you that information. And it has a very similar idea as using curvefit. It just gives you the extra information. This one is a little more sophisticated, so it goes all the way back to scipy.optimize.least squares, which is what happens in curvefit one level back. And down here it has, some ideas of extending, same idea of extending curvefit to let you do other things. All I want to do in this video is kind of walk through what it looks like and how it's different and whether it is the right thing for you to do. So you'll probably have to pip install lmfit. It's usually not part of the built-in package. But we'll just import lmfit here. I've already done that. And the first thing we need to do is define a residuals function. So instead of defining a model, we directly define residuals here. And residuals is going to take an object called p, and we'll get to what p is in a minute. And this will return, we're going to use the model function that I wrote before, and we have to extract out the parameters by their names in here. All right, so this is the thing that we need to do, and then we're going to subtract y from it, so that this will be the error between the model and the known y values at these values of x. Now probably I should do this. Let's define the parse object first. So that's going to be lmfit.parameters. And this is one place where lmfit really deviates from the really simple function-based model in scipy. This is now a class. It's an instance of a class, and we have to call a function on it to add many parameters. And here we can get away in this case with just adding tuples. So I'm adding a parameter called a with an initial value of 200 and another parameter called b, and we'll give it an initial value of 1. All right, and so this is going to create a parse object and then add these parameters to it. And the parse is what is going to go into p here, and then we can extract it out like it's a dictionary. All right, a couple more steps. We now have to define the minimizer. Let's call it mini. And this is another kind of object called lmfit minimizer. And it takes the residuals function and the parse object to initialize it. And then we have to run it. So we'll say the result is equal to mini.minimize. And this will vary the parameters to minimize the residuals. And then finally, we're going to print the fit report. So lmfit.fit report, and we just pass it the result.params like this. All right, so it's still a fairly small number of lines of code, partly because I defined this model up here before, but you could define it directly with these if you wanted. I just am not doing that here. All right, so what does that give us? This gives us the variables a, and they're the same numbers that we saw before, I think. Let's check. 809, 88, yep, these look pretty much exactly the same as the numbers we saw before in both cases, and that, again, shouldn't be too surprising. We are not changing the model or anything like that. We should get it. And you see that it automatically is printing the plus or minus standard error on there. And these are the same numbers we got from the diagonal of that covariance matrix that you saw before. This is printing it in a little bit nicer way, but with a little bit of the overhead that you have to really read the documentation to see how do you construct these instances, and then how do you call these functions, and then how do you print this nice result in just a single line. All right, so these are not quite the same as the confidence intervals. This is just plus or minus the standard error, and it does provide a way to do that. So we'll just say ci is equal to lmfit .conf interval, and we have to give it the minimizer and the result, and then we can do lmfit and print functions, print funcs dot report. Underscore CI, and we print this object here. All right, and so let's see, what did I do? I did something not right there. Oh, I misspelled funcs. All right, so now we get the best value that's shown here. These correspond to the A and the B up here. And then if you want different confidence intervals on either side, so this is plus or minus 1 standard deviation, and you can see that we go from 12.35 to 14.32 once we account for the degrees of freedom that we have being only about 5. So this interval is bigger than just the standard error. And if you want 2 standard deviations, you get to minus 33.8, which is a little bit bigger than 2 times this, right? So you can see from here, plus or minus 1 is about 68%, plus or minus 2 is good enough, close enough to 95% for that, and the difference between 33 and 2 times 12 is about 24, is related to the uncertainty from the student t multipliers. All right, so what is 213 minus 33? I'll just copy this and let's calculate it. That gives you 179.96, and in the value we got up here, we got basically that same number, 179.5 for the plus or minus on here. So this is 95.45%. Let me come back up here and make this. This is 95%, not 95.45. So we need 0.05 is 95%, so 1 minus 0.9545. And that gives me something that is a little bit bigger, but now it's hard to read. All right, so we get 178.36, so it's still not quite exactly this. But it's pretty close. The difference is probably how they treat specifically degrees of freedom and whether they're normalizing by square root of n or square root of n minus 1 or something like that. That's most likely the reason. Okay, so what was the main point of today? The main point is nonlinear regression is not that difficult. Curve fit or least squares, any of those will give you the A and the B parameters with very little work. Here you define a model, you call curve fit. This gives you this p covariance, and I mentioned that the square root of the diagonal is related to the standard errors, and you can use that to estimate, really quickly and roughly what the standard deviation or standard error of your parameters are. And the more data points you have, the more reasonable that is. In this case, we don't have very many data points, and so the value we get at 213, we're not super sure, not super confident about that. It could actually be in the range of, say, plus or minus about 24 in this analysis. Then I showed you about nlinfit, which is just a wrapper around curve curve fit, and it does use the student t-value to figure out what the multiplier should be to expand or increase the uncertainty estimate. And then we looked at lmfit, which is a fully featured nonlinear regression package that does a lot of things that nlinfit doesn't do, and it may be helpful, but you have to learn and remember all of these different classes and objects and instances and methods, which makes it a little bit trickier to use, but might make it much more powerful and much easier to report these kinds of tables and variables and correlations and things like that. All right, so with that, I'll stop and see you next time.